Okay, let's take a look at dot products today with vectors. Uh, Probably the easiest way to just show you what a dot product is just to go through the process of finding one. Now, I'm going to add a video to this sequence in the next day or two that's going to show the applications of dot products. So today is just a mechanical. We may not understand what it's for. It's just getting comfortable in the mechanics. So when we get to the more challenging problems, we're equipped, we're ready to go. So just a mechanical practice day. So here we have two vectors, u. This is given in linear combination form. I'm going to write that in component form. That is 3, 2, of course. And v in component form is -2, 1, as we know. And to find the dot product, it looks just like multiplication, but we probably should say u dot v. If you say u times v, in effect, you're right. But it's not what you might think it is. It's not just, this does not equal multiply the x's, multiply the y's, and get this vector. In fact, it's not even going to end up being a vector at all. What we're to do, there is a horizontal component. We do multiply those, 3 times -2, but then there is a vertical component for each, and we multiply those, 2 times 1, and we add that result. So we get 3 times -2, -6 plus 2, -4. So this -4 is not a vector. It's actually, in vector land, it's called a scalar. The reason it's called a scalar is because if we multiply that by a vector, for instance, if I have something along the lines of 3 times the vector 4, 5, this vector 4, 5 is a vector that wants to slide things 4 to the right and up 5. And 3 just scales it. It says, let's, instead of sliding it 4 to the right and 5 up, let's do it 3 times that, or 12 to the right and 15 up. So anyway, there is our dot product. We take the horizontal components, multiply them. We take the vertical components, multiply them, and we add that result. And there's a number of applications for that, and we'll start hinting at those a little bit in today's lesson, but in a later video, you'll see more applications of dot products. Okay, so here we're to use some given vectors, and we're to find some solutions. Now, there are rules in our book that talk about what happens when we multiply this. Of course, this is a scalar but very, very simple, and it's pretty much what we would expect. So here we're supposed to take 4 times vector u, which is 2, 2, and find the dot product of that with vector v, -3, 4. Well, 4 is just scales our 2, 2 vector, which means instead of going right 2, up 2, we're going to go 4 times that, or right 8, up 8. And then we're going to dot that with -3, 4. So one more time, the long form of this, without doing any computation in our head, would be the 8 times the -3 plus the 8 times the 4, the product of the vertical components. Or in this case, -24 plus 32 for 8. In the book, it asks to determine, is our final solution a vector or a scalar? Well, this is just a plain old number, and a plain old number in vector land is called a scalar. Okay. Number 10. So we may suspect that, oh, anytime we do dot products, we end up getting scalars. Let's take a look. Here we have u, which is 2, 2, times 2 times v, which I'm going to take the liberty of working this one out. 2 times v would be 2 times -3, -6, 2 times 4, 8. And then we want to do the dot product of those and multiply those by w, or dot those with w, 1, -4. So let's go ahead and do some of this work in our head here. Here I get -12 plus 16. Is this a vector or is this a scalar? Well, it's the product of two vectors. I don't see any commas in here. Dot products become scalar. So this is just a scalar that then we're going to multiply by 1, -4. So that becomes 4 times 1, -4. But now I'm just scaling this vector. 4 times it, 4 times as big, 4 times as powerful, however you want to look at it, would become the vector for -16. So there is some dot product work going on in this problem, but we still end up with a vector. So this guy, our result, is a vector. And at this point right now, you should hopefully be kind of curious, when are we going to ever apply this stuff? That's coming. Okay, use the dot product to find the magnitude of u. Well, let's go ahead and find the magnitude of u without using dot products. U is a vector that wants to slide things to the right 6, or with a force of to the right 6 and a force of down 10. If I was going to do this graphically, it would be to the right 6, down 10. Over here at 6, -10. U looks like this. And how would we find the magnitude? Well, the magnitude's right here. It's this side. It's the length of this side. I'd probably real quickly just go through Pythagorean theorem. And I would say, well, that's going to be 6 squared plus -10 squared equals our hypotenuse squared, or the magnitude of our vector squared. So I'm just going to call that m for magnitude squared. So our magnitude is 136. It is the square root of 136, which of course we could probably break that down somewhat, but that's ultimately what our magnitude is. Now, if we take a look at what would u dot u be? This is kind of an interesting one. What if I went u dot u? We've got a rule for u dot u that we haven't talked about, but u dot u would just be 6 -10 dot 6 -10. Well, that would be 6 times 6 plus -10 times -10, and there we are. So all I would need to do to find the magnitude, because I've just found this, is take the square root of it. So we get square root again of 136 is our magnitude of u. So we see that u dot u actually gives us the magnitude squared. This formula right here is exactly Pythagorean theorem in vector land. Oftentimes we would use this as square root u dot u equals magnitude u. Be careful here. It's tempting to say that this is just u, but again, dot products, the product of vectors, dot products, are not the same as like saying square root of 7 squared. It's a little bit different in vector land. So really, really nice formula here, but basically it is just Pythagorean theorem. Here's a great formula that utilizes dot products. It tells us the cosine between angles is u dot v over magnitude u magnitude v. We can find the angle between two vectors using that formula. It is a really, really simple formula, and this thing is basically, in vector land, this formula is basically law of cosines. So let's go ahead and apply this. This is 2, -3, and this is a vector 1, -2. And if I was just to sketch those so we get some idea of what we're looking for here, I've got 2, -3. I've got this vector, and 1, negative 2, this vector. And what we're trying to find right here is theta. So we could say the cosine of theta using this formula is u dot v. And u dot v is just the product of the horizontals, 2, plus the product of the verticals, negative 3 times negative 2, 6, all on the magnitude. But the magnitude is just our Pythagorean theorem. And it's really, really simple. We could do this without looking at the diagram. It's just this distance 3, this distance 2, but they're right here. So the magnitude, Pythagorean theorem with those two distances is 2 squared 4, 3 squared, negative 3 squared 9, 13, square root of 13. That is magnitude of u. Magnitude of v, 1 squared 1 plus negative 2 squared 4, 1 plus 4, 5, root 5. We could get that by building this, but I don't think we need to do that. So theta is cosine inverse of 8 on root 65. And we would probably, normally when we're talking about angles between vectors or angles of triangles, very, very typically we would want those in degree measures. So we'd want to set our calculator in degrees more than likely, unless we had some evidence to the contrary. And then we just go ahead and find our theta, which I'll leave to the viewer. Okay, here we have basically the same problem, and this time it just asked us to go ahead and sketch our graph of this. So here we have u. Again, this sounds familiar. 2, negative 3. We have v in component form is 4, 3. If we were to sketch this, would have something along the lines of this. 1, 2, 3, 4. I need to go down 3. I need to go up 3. So I have 2, negative 3. There's vector u. I have 4, 3. There's vector v. And I'm going to go ahead and find theta, the angle between those two. So again, using this awesome formula that we have that says cosine of theta equals dot product uv over the product of the magnitudes. I'm looking for something that, if my diagram is fairly accurate and it's reasonable, boy, I'm looking for an angle that's going to be pretty close to 90 degrees. May not be 90, but should be pretty close to that. So I get u dot v. Let's do that one in our head. I get 8 plus negative 9, negative 1, on u, magnitude of u. Let's go magnitude of u. We're thinking Pythagorean theorem here. 4 and 9, root 13. 16 and 9, root 25, 5, or a 3, 4, 5 right triangle. So I end up with theta equals cosine inverse of negative 1 on 5 root 3. And I believe we end up with 93.18 degrees when we go to calculator on that, which pretty well confirms what I'm seeing here. We're somewhere close to 90 degrees. So just a great way. What would our option be to find that? Well, our option to find that would be, I could complete this triangle, find this distance, find this distance, find this distance, and then go law of cosines for that. And to be honest, we're really doing all of that. We're really going through all of that process when we do this, but it sure organizes it well. A great challenge problem would be to go ahead and set up in your calculator, if you've done any programming, go ahead and set up a prompt that asks the user, if you do your programming for a U1, a U2, a V1, a V2, and then you can use those to calculate what the angle is. And we've had a couple students do that today, and I think it only took maybe 3-4 minutes for them to set that up. Okay, so here we're just given ordered pairs of the vertices of triangles. I'm going to draw a sketch of this, of course. Might look something like I've got a point at -3, 0. I'm going to call that A. I got a point at 2, 2. I'm going to call that guy B. And I've got a point at 0, 6. I'm going to call C. And if we wanted to find our angles, angle A, angle B, angle C, if we wanted to find the measure of those, we would have to find like side B, side C, side A, those distances, and then law of cosines this from there, unless we had some other crafty approach to it. But we can go ahead and find angle A. Cosine of A equals the dot product of the vectors exiting angle A. And the vectors exiting angle A have horizontal and vertical components. If I call this V1, exiting angle A, that has a horizontal component of 5, a vertical component of 2. And if I call this V2, vector exiting angle A has a horizontal component of 3, a vertical component of 6. And then underneath that, I just want my magnitudes of these, which I'm going to just do in my head. Magnitude of a 5, 2 would be 25 and 4, 29. Magnitude of a 3, 6 would be 9 and 36, root 45. So angle A is cosine inverse of, let's take care of this dot product in our head. 5 times 2, 15, plus 2 times 6, 12. 15 and 12, 27 on root 29 times root 45. Make certain if you're doing this in your calculator that you wrap this denominator in parentheses, and then we should be able to find cosine A. And I think I'll go ahead and set up cosine inverse that. We should be able to find the measure of angle A. I think I'll go ahead and do angle B and then leave angle C for the reader. So cosine of angle B is the vector exiting angle B. This is our V1 in reverse. Now my horizontal component is -5. My vertical component from B down to A is -2. Dot that with this guy. Exiting angle B has a horizontal component -2, a vertical component up 4. On, let's do magnitudes, 25 and 4, 29, times 4 and 16, root 20. So angle B is equal to cosine inverse of, let's do this dot product in our head. That's 10 plus -8, 2 on root 29 times root 20. And of course, once we have angle B, which I'll leave to the viewer, once we have angle B and once we have angle A, we could subtract from 180 to find angle C, but it would probably be comforting to go ahead and find angle C with this new process and then see if our three angles do in fact add up to 180 degrees. But this guy, what a great way to find angle measures given two vectors, or in this case, the lengths of two sides of triangles that we kind of turn into vectors. So really, really good stuff. Okay, now we're to find u dot v. Well, interesting. I don't even know what u and v are, but I know they're magnitudes, and I've got a measure of an angle between vector u and vector v. So I can go back to this formula. that says cosine of the angle between them equals the dot product, u dot v, over the magnitudes, the product of the magnitudes, but that's given as 4 and 12. And really, all I'm trying to find is that guy, u dot v. So cosine pi on 3, well, that's a breeze. That's 1/2 equals u dot v on 48. Multiply 48 to both sides, and I get u dot v is 48 times 1/2, 24. I don't know what vector u is. I don't know what vector v is specifically in component form, but I do know that u dot v must be 24. So there you have a quick view of the introduction to dot products, and the next video is going to include some more in-depth, maybe using them to kind of grind out some real-world problems.